Welcome everyone, this is Jim Corkins and we are finishing our last instruction in the electric forces and electric charges area, which is the 1.0 module. Alright, so if you haven't done the reading, please do so. They will help you. Those readings are listed in your Canvas course. Now, before we get into this specific set of content, I just want to point out to you that it's probably going to be really helpful for you to review the Physics 111 or Physics 121 course content on 2D force diagrams. So that link is in your notes, but it's also in the Canvas course. It'll be really helpful for you to review that. All right? Now, moving on, here we have all of our different forces that we're going to be working with in our course. So, just to review, here, these top two are now going to be called our non-contact forces. So, these two are our non-contact forces. The first one is the weight of the earth, that is your weight, the earth pulling down on you. So that's the first non-contact force. Non-contact meaning the object doesn't have to physically touch you in order to create a force on you. All other forces are contact forces. So mass times gravity in your 121 and 111, that was the non-contact force. And now we have a second non-contact force, which is the electric force. It's the Coulomb force, which is Q1 KQ2 over R squared. Now, all the rest of these forces, everything else, has to be physically touching you. So these are called contact forces. So a good method is when you're doing these problems that we're going to be doing, where we're now bringing in your old forces from your Physics 111, Physics 121 content into the Coulomb force forces that we've been studying this whole time. So once you get these two non-contact forces out of the way, then you just ask yourself, what is physically touching your object? Okay. Is it a force that you can't really subscript it as it's just a push or a pull, like a hand or a foot? Is it a rope or a string? So is it a tension, and that always pulls you? Is it a spring, which is K times X, the spring constant times X? Don't make the mistake of the spring constant being the same thing as this constant, which is 9 times 10 to the 9th Newton meter squared per Coulomb squared. So the spring constant is how stiff the spring is. X is how far it's compressed or stretched from the equilibrium position. And then finally you have a surface, which creates two different types of forces. It creates a normal force, which is perpendicular to the surface. And that's basically the surface holding up the object, right? But then you have a force that is parallel to the surface, which is called friction, okay? And that's mu sub k times the normal force if it's moving, or mu sub s times the normal force if it is not moving, all right? So friction force is parallel to the surface, while the normal force is perpendicular. So anytime an object is touching a surface, it's probably got two forces on it. It's probably got the normal force and friction. Okay? Now, if you are having trouble following this, again, I cannot stress this enough. Please go to the link in the Canvas course or in the notes. Click on this little picture of the video, and it'll send you out to that review. All right. Now, let's go ahead and do an example problem. All right. Here we have two objects. One is a Q2, which is positive 10 nanocoulombs, and we have a Q1, which is negative 10 nanocoulombs. We want to know what the normal force is acting on this positive Q2 object, okay? Or if one exists, all right? So we're going to go through all the steps. Now, both of these objects are a distance 1 centimeter apart, and the glass bead has a mass of 0.15 kilograms, right? So starting off, just like we always do, we're going to go ahead and write our coordinate system, right? Eventually, when anytime you're doing vector addition or subtraction, you should write down a coordinate system. So this is going to be positive x, positive y, negative x, and negative y. At the center of this, I'm going to put positive 10 nanocoulombs. That's 10 to the negative 9th coulombs. And a mass of 0.15 kilograms. Okay, so I'm putting the important information for our object right there. Now, let's go ahead and talk about the contact forces. This object will have a mass pulling it down. The Earth will be pulling it down. And so that's the mass times gravity. And while I'm here, I'm just actually going to go ahead and write in negative 0.15 kilograms times 9.8. Meters per second squared, right? So that is the weight of the object, okay? Okay, which I will scooch this over so it's right underneath this. You don't have to do that, right? You could just write negative mg, but you do have to label your vectors and also put the directions on them as plus or minus. Okay, the other non-contact force is the Coulomb force. Okay, in this case, we have that kind of orangey gold color bead, Q1, pulling up on our object. So that doesn't have I'll make it purple. It's pulling up on our charge, and that force is positive, and that is going to be negative 10 nanocoulombs, comma 0.01 meters. And go ahead and convert to meters if you have the chance. Okay. Finally, so we've got our two forces out of the way, right? In fact, what I'm going to do is I'm going to grab this and bring it over so you can see what I'm thinking about. Hold on one moment. So we just completed our two. So we just finished our two non-contact forces. Now we're going to go through this like a checklist. Now, looking at this blue charge right here, is there a hand or a foot or another random force physically touching it? No. Is there a rope or a string touching it? No. Is there a spring touching it? Yes. No, there is not a spring touching it. Is a surface touching it? Yes. Okay, so yes, so that surface means it's going to have a normal force on it. But is this object moving left or right, or is it being pulled left or right such that friction will exist, right? In order for friction to exist, it's got to be moving parallel to the surface, or a force has to be working on it parallel to the surface, in this case in the x direction. So no, there's not going to be any friction. So the only force that's in contact with this blue glass ball is the normal force. Okay? And I go through that in more detail in that video from that I've linked to this. So we're going to call this, I'm going to just write another up arrow. So the normal force is perpendicular to the surface, which is why they call it normal. Normal meaning perpendicular. So this is our force diagram. Okay? Now, we don't need to sum the forces in the x direction because there are no forces in the x direction. But we are going to sum the forces in the y direction. Whenever I sum the forces in the y direction, in our case now, since we are introducing those other forces, I'm going to note the velocity. It's not moving in the y direction at that moment. And it is not accelerating at that moment, right? We're not sure if it's going to be accelerating upwards or not. So I'm just going to put this acceleration is, I don't know. It depends on how these forces are working out. Okay? And in fact, they said the small glass bead is at rest. So actually, we do know that the small glass bead has no acceleration acting on it. All right. Now that I've got this written out, I'm going to take all this and copy it down here. So the first thing I'm going to do is write this. This is the normal force. So I got that one. Now I'm going to do the purple force. The purple force is pointing up. That black charge is what we're doing our force diagram on. That's 10 nanocoulombs. And that's being acted on by a negative 10 nanocoulombs. That is a distance 0.01 meters away. And now let's go ahead and let's rate this. Our negative mg is going to be minus 0.15 kilograms, okay, times 9.8 meters per second squared. Now, the negative here comes from the vector. 9.8 is not negative or positive. It is just a number. Okay, the negative comes from the direction of that vector, so that's why I put the negative in front of this. Now this is going to equal to the mass of the object, which we know is 0.15 kilograms, times the acceleration in the y direction, which we know is 0. So this is going to be equal to 0. Okay. Now let's go ahead and let's fine-tune this. Okay, we're going to turn these into numbers. Okay, so we have our normal force, which is right here. It's positive. Now that purple force, we're going to multiply this out. So that's going to be positive, and I'll put K times 10 nanocoulombs, and I'll make that black, nanocoulombs, times 10 nanocoulombs, all divided by 1 centimeter squared. Oh. 0.001. meters squared. Okay, now I'm going to multiply and find out its weight. So 0.15 times 9.8. So that's going to be negative 1.47. And that is just in newtons. Okay? Now let's figure out what this purple force is. So positive F sub n. And let's go ahead and let's turn this into a number. So this is 10 times 10 times 9 times 10 to the ninth. So here's what I'm seeing. We have 9 times 10 to the ninth Newton meters squared per Coulomb squared times 10 times 10 to the negative ninth coulombs, and I should make that black. Will be 10 times 10 to the negative ninth coulombs times 10 times 10 to the negative ninth coulombs all over 0.001 meters, 0.001 meters squared. Now what I can do is turn this into a number, okay? So let me show you what I mean. So this 0.001, I'm actually going to turn that into an exponent, and I'll show you why in a second. So that's 1 times 10, and it's 1, 2, 3, 4. So that's negative fourth meters squared. Minus 1.47 newtons. And equals 0. All right. Here's how a quick way to do this. So I'm going to write this over here. Here's what I see. Whenever I'm working with exponents, I take the solid numbers like the 10, 10 divided by 1, and I separate them by the 10 to the all these numbers. So when you multiply exponents against each other, what you're doing is you're actually adding them. Minus 9, so 9 minus 9 minus another 9. Now a negative 4 on the bottom is going to be a plus 4 when you bring it up top. Okay? So this is 900. Okay? And times 10, and then this is going to be negative 9 plus 4, which is going to be negative fifth, right? So that's how you do that. I just took the 9, 10, and 10 and brought it to the front, and this 10 is that black 10, and then I just took all those exponents, 9, negative 9, and negative 9, and put it right up top here, and a negative 4 on the bottom. When you bring it up top, it becomes a positive 4. All right? So now we have that nice and organized. Plus 900 times 10 to the negative fifth newtons plus, minus 1.47 newtons. And that's going to be equals to 0. Okay? Now let's figure out what this is. We're going to go 900 times, and I'm going to go bracket exponential, nope, that'll be 5 negative exponential equals, oops, oh, you know what, I don't know what I'm doing, I'm so sorry. I should just use, I don't know why I hit exponential right there. Let's try that again. 900 times bracket, I'm going to put 5 negative and click that, and bracket equals. So this is the 900 times 10 to the negative 5th, right? 1, 2, 3, and so that would just be no, actually 1, 2. So there'd be 9 times 10 to the negative 2. So anyways, now we're gonna subtract from that 1.47 equals. So that's negative 1.461. So F sub n minus 1.461 newtons equals 0. So that is going to be 1.46 newtons. Round to the second place, to the hundredths. So in these tutorials, I want you to round to the hundredths. And so that's how much the normal force is going to be acting on it. So, all right. So that's an example on how to do these problems. All right. If you need more help with this, again, you're just kind of adding your Coulomb force into this stuff. Don't forget to watch that video, which is a review of your physics 1 content on 2D force diagrams. Okay, it's very helpful. All right, I hope you have a great day. Thank you very much.